last class is going to be on what I consider to be a social and political question masquerading as a science question, but one which I think is very, very interesting when you drill down into it for understanding the complexities of the relationship between culture, society, and property. And this is property and the environment. Now, as we go through this, I expect that you guys will be saying, oh my goodness, why is he finishing this series with a lecture on the environment? We've had this ever since we were watching Sesame Street, or wherever it was we were watching when you were 3 or 4 years old. Okay? You know it all, forwards and backwards and sideways and all the rest of it. So why are we talking about it here? I'm going to be talking a little bit about science, and a lot more, I hope, once we deal with the science, about issues relating to social process, the way that ideas float around, and the power of ideas, even when they are cut loose from the narrow confines of natural science. So we're going to be looking at, if you like, the politics of environmentalism. And that has a huge impact on property and property rights. Probably not so much for you folks who probably see yourselves spending your professional careers in a city at least as big as Sydney. But if you have a bit of a hankering for the wide open spaces and think about practicing as a property economist, say in Dubbo or Wagga or some regional part of Australia, where incidentally there's an awfully good life to be made as a property economist, and out there the valuers and the developers and whatnot are more grey-haired than I am, and they're looking for young talent, and real estate is cheaper. You can even have a family. So that's the plug before going bush, right? But one of the other curious things about it is that things like water property, carbon property, and environmental protections are growing teeth to the extent that property rights are changing. I think they are being constrained somewhat to the extent, I may have mentioned, that in various parts of Australia, if you let the weeds get too high, you're never allowed to cut them down. Other parts of Australia, if you want to plant something, the only thing you can plant is not the kind of crops that have been planted in an area for generations and generations. The only thing you can plant a seed for is the local native plants. And that means that from a farmer's point of view, the land becomes useless. This is happening in our time. All because we believe that that's a good thing to do for our grandchildren. And so that's why we're going to be looking at this question. It's an ethical question ultimately, and I think not so long ago we were talking about what ethics is and how it works, and so I'm going to be looking a bit at ethics. Okay. It's important, I think, to be able to pass on to future generations something similar to what our generation, your generation, has received. This is a very big theme amongst Indigenous people. It's a theme which hasn't been a part of Western thinking for a long time. I think it was back around at the beginning of modernity, or maybe a little earlier. But over the last few hundred years, it's kind of faded out, and so we don't mind mining things and leaving a lot of rubbish around and, polluting the waterways and the airways and all the rest of it. But that does have an impact on the future. So that impact is negative to the extent that a future generation won't have those resources in the ground, and they may have dirty air, dirty water, dirty fields and whatnot. They're bad things. Equally bad, though, is locking away things which don't need to be locked away. Something like about 150 years ago, some people in Britain were extremely concerned about a huge looming environmental problem, which was the prospects of running out of energy. And the reason was they projected their use of energy into the future, and they worked out that somewhere around at the end of the century, England was going to run out of coal, because they looked at their coal reserves, they looked at their consumption, they looked at the rise in consumption, and they said, "Ooh, by the end of the century, we're going to run out of coal. What are we going to do?" And it was a major problem. That was in the middle of the 1800s. If the science behind their concern was true, was valid, England would not have any coal today. No coal mines anywhere in the British Isles. But through the 20th century, guess what? Huge amounts of the stuff. That is until we get to about the middle of the, or about 2/3 of the way into the 20th century, where oddly enough, exactly the same problem arose again. Many people were saying, we're about to run out of coal. This is a really bad thing. When I was an undergraduate, sitting in classes a bit like this, although not with the technology, over at UNSW in the early 70s, 1970s that is, we were told that by the end of the century, Australia would have no coal at all. And in the early 70s, we were also being convinced that by the end of the decade, in other words, by 1980, that's before most of you guys were born, the world was going to run out of oil. And I remember being a young, zealous university student, telling a friend of mine, he was actually a senior surveyor in the office that I was working with part-time, that it was probably a waste of time in buying his new car, because the thing would hardly be worn in, or at least worn out, and there wouldn't be any oil to go and run in it. That was in the early 70s. Okay. Now, have we run out of oil? No. Have we run out of coal? Last time I had a close look, which was actually around 2000, I thought back to the 70s when I was an undergraduate and a bit of a zealous in this regard. And my kids were doing a school project on energy. And the coal board, or whatever it was in Australia, had sent some of my kids some project material. And they said that on the basis of current known reserves, current usage, and the current trends in expansion of usage, Australia had sufficient coal for about the next 2 to 3 centuries. That was the opinion in the year 2000. Hardly run out. Now, if we had introduced punitive legislation or controls or what have you back then to limit our use of coal, what would the result have been? It certainly wouldn't have helped our standard of living today. And so silly science is capable of resulting in silly conclusions and sometimes silly legislation and social change. We have to get the science right. When we look at environmental problems, we can break them into what I would consider to be 2 groups. There are serious environmental problems that have popped up from time to time. One group of those problems is what I would call management issues. And I call them management issues because they have to do with places where it is prudent to manage the way we use things and do things in a way which might be better to how we started. For instance, there was a time when things like coal-fired electricity generators and other factories that used coal poured out a lot of sooty smoke, and that caused lots of problems all over the place. Respiratory problems for people and animals. It caused problems for the landscape, it caused problems for farms, caused lots and lots of problems. There's a management problem though. How do you get rid of the sooty smoke? Well, with a bit of technology, it works out that it's not too hard to put into your smokestacks, your chimneys, things that are now fairly standard, electrostatic, basically sieves almost, that take out all of those particles. And what goes out of your smokestack then is simply, a natural gas. Right? And so by managing these problems, we're able to overcome them. It's been said that humans make garbage, but they almost also make garbage bins. We can solve a lot of these problems by improving our management. So things like packaging, industrial emissions, which I've just been talking about, contaminated land, forestry, water supply, and so on, are all things that can be managed. And the impressive thing is that we've learned how to manage them very well. It means that the question has really got to do with, it's a technical matter. But that's different to global problems. Global problems have a different nature. They tend to come from a mantra, a chorus, that goes something like, humans are a dreadful virus that is afflicting the earth, and the world would be a lot better off without them. And as a result of humans, we're doing dreadful things that poor old earth doesn't really, cope with very well. The problems have to do with unsustainability. Some years ago, this university decided to take on board the theme of sustainability. And when we sat around as a faculty, design, architecture and building, we sat around and said, well, what does sustainability mean? And we ended up with so many definitions of it. Social sustainability, physical sustainability, environmental sustainability, this sustainability, that sustainability, something else sustainability. Sustainability ended up looking so big, so broad, that you can simply refer or relate or replace the word sustainability by a far simpler and older word, good. Sustainable practices, good practices, And so it's sort of everything but nothing. But the problem with the global solutions, and this is one of the curious things, when I first started giving this class, which has long been a part of this series, I used to come in wearing a white dust coat and heavy rimmed glasses and carrying a clipboard and try my hardest to look the nerdy scientist, you see. And it was kind of good for a laugh to start off. But it had to do with our belief in a particular approach to science. And when you look at the books that are written in this area, and one of the books I usually bring in was a book by a gentleman by the name of John Horton, who went on to become very rich and probably very famous in the environmental area, as he worked for the United Nations and was given lots of speaking tours and whatnot. His book was on global warming. We talked about global warming back in the 90s. We now talk about climate change. It's actually the same thing, but the problem with people talking about global warming is that we haven't had global warming on the planet for about 20 years, so we can't actually use the same type of, the same term. But Horton's conclusion was very simple. After he went through all of the gloom and doom about how carbon dioxide was going to kill us, his solution was population control. And you find, when you get to the end of the book, that it's all about the science of how gases work and sort of the precipitation cycle and that sort of stuff. When the conclusion is ride bicycles and cut down your population, you think, hang on, we're actually talking about something different here. We're not talking about carbon dioxide at all. We're talking about a eugenics agenda, which is a very social, political issue. It really doesn't have to do nearly as much with the environment as we first thought. And back in the 80s and 90s, and I haven't been reading a lot of the literature since then as wide as I'm used to them, but as far as I have seen, and what I have seen is that basically the solutions are still the same, regardless of whether we're talking about ozone, which is a little bit passé now, or species depletion, or deforestation, or what have you. The solution tends to be get rid of the people. And so this global problem seemed to have this different nature. But we can talk about all these different environmental problems, but the solution is always a political, social solution. And that's completely different putting in screening systems in the chimneys or recycling plastic bags or something. Completely different. I've already talked to you about the 1830s coal crisis and how it was a bit of a non-event. I'll go over some of the rather adventurous environmental problems that we had when I was your age. Around 1970, the major climate problem was the imminent ice age. We were all going to freeze to death, and so we'd have to be moving up to the tropics to be able to find a place where we'd be able to plant our crops and so on. It's curious because if you read geologists, and I used to be able to mention a number of authors off the top of my head, hopefully they'll come back to me shortly, the likelihood of the planet going into an ice age is actually very high. And it could tip into an ice age very quickly, over a period of about 70 years. So, for instance, if it started to go in that direction, if in 1998, when the planet started to cool, or at least its most recent cooling phase, that was the beginning of our next ice age, by the time you guys are my age, you might have to move up to the tropics. But people don't talk about the coming ice age very much after about 1980, because a new problem came on. I've mentioned oil to run out by 1980 and also coal going to disappear and things like that. In the 1970s, people were talking about sea level rise. That has become a bit of an interest of mine ever since. I think the last time I published on it was now probably about 5 years ago or so. Around the 1970s, we were expecting about a 1.5 metre rise in the sea level by the turn of the century. That means you'd be hopping on your Manly ferry from about, the AMP building. Hasn't happened. But that's what we were being told back in 1970 or in the 1970s. There was also the expectation, and people are getting quite concerned about this, about widespread starvation. We were going to run out of food. The results have been just the opposite. We now have to pour an awful lot of the stuff into the ocean to go and keep the food markets kind of paying the right kind of prices for grain. Widespread deforestation by 2000. Oddly enough, by 2000, we had more forests globally than we had in 1970. And the serious species depletion. A lot of those things we don't talk about anymore because they have been shown to be embarrassingly silly. For instance, species depletion, we're talking about thousands of species kind of being, just sort of, snubbed out of existence. And yet, when we actually looked at the number of species that were depleted through the 20th century, the number is less than 20. A long way short of the thousands that we're talking about. In this picture here, and it's a common one, in fact it was taken off the webpage of the Australian Greenhouse Office website a couple of years ago now. And it was meant to make us concerned about CO2. Now you'll notice the caption down there. While it looks like all these dreadful gases are being poured into the atmosphere, it's actually steam carbon dioxide you don't see. But yet that's the way that we're introduced to this idea, seeing these huge expanses of industrial horror, putting these toxic gases into the air. I'm going to be talking a fair bit now about carbon dioxide. One of the things that we have noticed is that there is a correlation between the Earth's temperature and carbon dioxide levels. We say, oh, that's no good. And a lot of people are of the opinion that if we increase our carbon dioxide levels, the temperature will increase, because we can look at those correlations over a long period of time. It turns out that over the last century or so, we have been producing a lot more carbon dioxide than we had in previous centuries. I'm going to look at the global temperature record for a moment through this last century, where we've been producing lots and lots of carbon dioxide. We produced a lot more carbon dioxide this side of the Second World War. In fact, if you look at the 1930s, most people still didn't have motor cars. Come back after the Second World War, and suddenly motor cars were being used all over the place. We were using considerably more industrialisation, trucks and whatnot to move things around, large-scale agricultural machinery and so on. The odd thing about it is that while we look at this graph, and we can see that since about 1860, 1880, the Earth's temperature has risen. We go about 1860 up to about year 2000 roughly. Actually 1998 is the key date. You say yes, the Earth's temperature has been rising. And during that century, a lot more carbon dioxide has gone into the atmosphere. But the odd thing is, I'll just go back one. The odd thing is that even though we've had that century of increasing carbon dioxide, through that century, we've had long periods of time when the temperature has actually been falling. Now, while there's a noticeable period in the early part of the century, which incidentally was also a time around the First World War where there was a bit of a nudge in carbon dioxide production because of industrialisation around the First World War. The really curious one is what happened after the Second World War, at the period where the carbon dioxide levels were going through the roof, but the global temperatures were falling. And I've mentioned before that from 1998 onwards, that's 20 years ago, the global temperatures have been on a downward trend. I'm not sure if they're going to continue on a downward trend for a long period of time. They might start to go up again in another few years, I don't know. But the one thing I do know is that it doesn't actually augur well for someone arguing that if you increase carbon dioxide levels, we're going to increase the temperature. I don't think I've got graphs of this, but if I was to put up a graph showing the intensity of sunspots over the same period, I would find a line which tracks very closely to that one. I'm not going to go any further down that because I want to look more at the whole process of carbon dioxide. Okay? But just be on notice that somehow carbon dioxide and sunspots are related, and I do not think that carbon dioxide reduction on the Earth is actually causing the sun to change. It might just be the other way around. When we look at the numbers that we're interested in, we have seen about 0.6 of a degree increase in temperature over the last century or so. But let's look at that in terms of seasonal variation. On this graph is the year-by-year changes in average temperature, or at least decade by decade, over a century or so. And what we have there is the seasonal variation. The point of this graph is that the 0.6 of a degree of overall warming that happened through the 20th century actually gets lost when you look at the annual variation. It's almost nothing more than noise. Because year by year, sometimes you'll have a warm year, sometimes you'll have a cool year. And if you take a long-term average, there's a slight change. There's an awful lot of noise in the data. Let's drill down a little bit further. If we look at the last 2,000 years, and this was one of the graphs which I found curious when I first started to take interest in this. I guess this is it's been an interest of mine now for about 20 years. And when I first looked at it at the end of the 90s, this is before this last cooling phase kind of came on, one of the things which was in all of the data back then was a thing called the medieval warm period. Medieval warm period is an important part of history when back around the medieval era, 10th, 11th, 12th centuries, the planet generally was a lot warmer. When adventurers sailed across and discovered Iceland and Greenland, while they named Iceland appropriately for how it looks today, Greenland's a bit of an anomaly because now it looks more like Iceland. But in the medieval ages, when they were first sailing ships over there, it was a green land, and that's why they called it that. It's because of this lump of temperatures back around the Middle Ages. And so there were things that could be grown in the British Isles that can't grow there anymore. Now, why am I mentioning the medieval war period? Because it fits into this longer history of the Earth's climate. And it would say that while the Earth has been warming up this side of, let's say, 1860s, the reason the 1860s is usually used as the starting point for a lot of these graphs is it was only in the 1860s that we had enough temperature gauges spread around the world that we could actually measure the Earth's temperature relatively accurately using direct methods. These temperature estimates come from indirect methods. Things like looking at the chemistry of old deposits of ice in places like the poles and other places. Also tree rings in very old forests. They tell us something about the temperature. Some of these indirect measures of temperature are more effective, more precise than others. And so we're able to work out what the historical temperatures were from things like tree rings and various depositions and so on. And that was the graph that was around when I first started taking interest in it. But then an odd thing happened. In 1998, a group of researchers produced this lower graph of the Earth's temperature over the last 1,000 years or so, done by a chap by the name of Mann and his team, Mann et al. And it was important because all of a sudden, instead of having our current trend in temperature, which is just this part here, as something which is just part of, the waxing and waning and maybe returning to, maybe in another 50 or 100 years or something, we might get up to the temperatures it was during the medieval warm period. You notice that on this graph, medieval period, what's not there? No lump. It gave us a thing which is now called the hockey stick curve. Mann's hockey stick curve. In other words, a straight stick with a little hook on the end of it. And this hook is the dreadful things that we horrid humans are doing by driving our cars to work rather than riding a bicycle. And that's going to kill us. Very, very important that man was able to put that graph together because it was very, very important for proving that carbon dioxide is related to the Earth's temperature. There's a bit of a problem though. A number of chaps, and they were Australians, McIntyre and McKittrick, showed that when Mann et al. Did their studies, they supposedly did a meta-analysis where they took all of these different indirect time series or temperature series And when they averaged them all together, the reliable ones and the unreliable ones, they applied interesting weightings. In fact, they applied weightings of over 300 times to those temperature series which pulled away or didn't have the medieval warm period in it. And so by using a particular time series that came from a particular pine tree, they were able to take the medieval warm period out. All they had to do was weight it by 300 times more importantly than the ice core samples and the other ones. The only downside to that is that generally it's accepted, or it was accepted up until 1998, that the ice core temperature inferences were considerably more reliable than these bristlecone pine trees. Why did man do it? Was it to do good science or something else? I'll let you to puzzle that yourselves. Okay. Conclusion from the medieval warm period is that we're now in an uncommonly warm period. We are coming into a period which is getting close to the medieval warm period. When we go back and look over a longer period of time, again using these indirect inferences of temperature, taken largely from ice core samples, in other words, drilling down in the Antarctic to very old ice, looking at the oxygen concentrations and other gas concentrations that's dissolved in the ice, are able to infer what the Earth's temperature was at various times in history. Okay, and this is a graph of our temperatures back about almost 500,000 years ago, 400,000 years ago. And here we are up here over the last couple of thousand, or last few thousand. And notice what this point here is looking like. How does that point compare to the whole graph? It looks like there are rare times in the Earth's history, about 4 or 5 of them in the last 500,000 years, 1, 2, 3, 4, 5 times, when the Earth has been warm enough to be able to grow apple trees in Tasmania. Most of the time it would be just under an ice sheet. And we happen to be living in one of them, and that's fantastic. I like living here, I don't know if I'd like to live there. Okay. So we are historically in an uncommonly warm period. Historically, the warm periods don't last a long time. This first one is a little bit wide. Some of them only last for a relatively short period of time, a few centuries or something, and they go back into this long period of coldness. We're at the end of a relatively wide one. Okay. Should we be afraid of global warming if this is the long-term average? And if we get really hot, we're likely to be doing something else shortly? Okay. Let's now look at how this carbon dioxide really does work. The Earth's temperature is kept as comfortable as it is because unlike the temperature in space, which is about minus 270 degrees Celsius, the surface of the world Earth is about 15 degrees Celsius overall, averaging between the tropics and the poles, which is pretty comfortable. It does that because there's a greenhouse layer of gases in our upper atmosphere. And those greenhouse layer of gases is very important because they trap the sun's energy. Now you've seen graphs like this before, okay? But I want to take this a little bit deeper, okay? What's happening here? Relatively high frequency energy comes in, it hits the surface of the Earth, it fluoresces, it's changed into a lower frequency heat, and then it's radiated back out. But because it gets up to this greenhouse layer, the greenhouse layer is transparent for the high frequency energy, but opaque, in fact a reflector, low frequency. Now this is not exactly a mirror. It's a vague, foggy cloud. But the energy can't get through it. What tends to happen is that the energy rattles around in here, some of it gets out, but a lot of it gets trapped under the greenhouse layer. That makes it a very comfortable place to live underneath. If you guys ever go flying in aeroplanes and they've got the trip data kind of on, look at the outside temperature at the cruising altitude of our normal commercial aeroplanes. It's about minus 50 degrees Celsius. Okay. Why is that? Because commercial aeroplanes fly on the top edge of this stuff. Okay. Not as cold as out there, but certainly not nearly as comfortable. Okay. So this thing is very, very important. There are a few curiosities about it. One is that while this process is important, because the reflection, the capturing by this thermal blanket is happening in this vague space of hundreds of metres of gas, as the reflected energy is rattling around in here and being trapped, scientists have predicted, they know, that the most intense area of greenhouse warming will actually be in the greenhouse layer itself. Right? And you get just a little bit of common sense will give you an idea of why. Because it's not a mirror. Right? Because there's an awful lot of energy being caught up in there. That trapped energy gave rise to the expectation of what's called the mid-altitude warmer spot. And from the 1990s, roughly, onwards, scientists have been working very hard to observe the mid-altitude hotspot, because that was going to be the signature, the indication, the sure fingerprint that it was the greenhouse layer intensifying that was causing the change in the Earth's temperature. And so the one way to prove 100% definitively that carbon dioxide was affecting the Earth's temperature was to go in search of the mid-altitude hotspot. Australia was involved in that task as much as other parts of the world. Our Australian Greenhouse Office and the scientific institutions that were a part of it were all up there analysing data from satellites and from high altitude weather balloons and all sorts of things. And they were looking at that for years. One of the gentlemen, one of the scientists that was looking at, was a gentleman by the name of David Evans. David Evans worked for Australian Greenhouse Office, and he pored over all this temperature data, and he was looking at the way that this upper atmosphere was warming up, because he wanted to find the hotspot, because then they could say definitively that it was carbon dioxide and the greenhouse layer changing that was resulting in the warming on the planet. What happened? He looked and looked and looked for years. He got paid well, but eventually he had to go with the data. And the data shows that there was no mid-altitude hotspot. The Earth was getting warmer, but the mid-altitude hotspot wasn't there. And these images show what it was supposed to be, what it was, in fact what it wasn't. And so Evans had a choice to stay with his well-paid, cushy job as a scientist working for the Australian Greenhouse Office, or to actually talk about what was happening. And the more he talked about what was happening, the less his employers liked him, and eventually he lost his job because he was out there publishing quite reputable scientific articles showing that the mid-altitude hotspot did not exist. And if the mid-altitude hotspot did not exist, one thing you can deduce quite conclusively is that whatever was causing the planet to warm up, it was not greenhouse change. Okay, and some of this has got to do with Evans and stuff. Evans is also an Australian, and so I guess I'm probably a little bit patriotic, and there have been a number of good people doing this kind of study. Evans lost his job because he wasn't willing to go along with what he considered to be most unscientific. Now, we looked at the long-term temperature record earlier on, and we said that currently we're in an uncharacteristically warm period of the Earth's history, at least looking over the last 500,000 years or 400,000 years. Now, there's something else you can get from this long-term history, and that is that you can see that over long-term history there is a correlation between carbon dioxide concentrations in the atmosphere and the Earth's temperature. The only problem is that the carbon dioxide concentrations historically have happened after the temperature has risen or fallen, not before it. It's pretty hard to argue causality when the supposed cause is happening something like 40,000 years after the supposed effect. Yes, the Earth's temperature has risen, and then a few tens of thousands of years later, the carbon dioxide levels have risen as well. What's causing what? The same thing happens on the downswing. A little bit of a surprise, but it really beggars the imagination to say that carbon dioxide is the cause and not the effect. We can move then to looking at the makeup of the greenhouse layer. We're told that carbon dioxide is an important greenhouse gas. What we're not told often is that there are many other greenhouse gases as well. Water vapour, for instance, is a greenhouse gas, at least as important as carbon dioxide, at least in terms of its effectiveness. However, there's a bit of a difference in terms of the concentrations of water vapour in the atmosphere compared to carbon dioxide. Carbon dioxide occupies concentrations of a few hundred parts per million. Water vapour is something like, I think about point something of a percent. It's parts per thousand. It's at least an order of magnitude greater. And on these pie charts, you can see the relative importance of carbon dioxide compared to water vapour and other greenhouse gases. And what we can see is that carbon dioxide is a very tiny player. The other thing about carbon dioxide is that it's subject to an awful lot of natural variation. All we need on the planet is for a nasty volcano to erupt, and suddenly we'll find productions globally of carbon dioxide many times greater than all of the human production of the stuff put together. And we look historically at when we have had major volcanic eruptions, a couple of things we can see that come as a result. One is that there are effects on the Earth's climate, but also those effects tend to mitigate over a relatively short period of time. And the reason is that the Earth is very good at absorbing imbalances or excesses or what have you of carbon dioxide. The environment in particular is very hungry for carbon dioxide. One of the curiosities is that we have roughly doubled our atmospheric carbon dioxide concentration. However, even though we've gone from about, I think it's about 250-ish parts per million of carbon dioxide in the atmosphere to a number in the high 300s, a fair bit more. When people, scientists, have had a very careful look at how much fossil fuel we have burned over the same period, the curious thing is that most of the carbon dioxide that was released as a result of our fossil fuel consumption has disappeared. And that was the puzzle. Yes, we have increased the atmospheric carbon dioxide levels, but not nearly as much as we should have, considering what we've been doing. The answer to that puzzle was found in places like Siberia and high altitude locations around the world, where it was discovered that there were forests growing up on the Russian steppes in places where trees never grew before. And one supposed it was too cold. Except that carbon dioxide is like a super fertiliser for plants. We're finding a lot of trees at altitudes now that they didn't used to grow. And so we talk about the tree line. As you go up steep, like tall mountains, you get to a point where the trees don't grow. I mean, it's just grass and stuff. And it's this particular level. It depends on where the mountains are. Now the tree line is actually higher because the increased carbon dioxide has given the trees that extra little oomph to be able to grow in unexpected places. And it's absorbed an awful lot of the planet's carbon dioxide excess, if excess it was. It turns out that the other thing that carbon dioxide does to plants is it makes them a lot more resilient to inconveniences like being on the edge of a desert. I once got into a conversation with a friend of mine who was very concerned about the problems to the environment as a result of carbon dioxide coming into the planet. And I said, gee, you know, one of the big problems we're going to have shortly is all this carbon dioxide is actually going to ruin our deserts. She said, oh, really? I said, yes. What used to be semi-arid in Australia has now got a lot more vegetation than ever used to before. Because if you feed plants a lot of carbon dioxide, they don't need as much water. And so plants are able to live in semi-desert locations. Now, commercial greenhouses use things called carbon dioxide generators, which is basically something like your propane barbecue kind of burner that just basically blows carbon dioxide into the big greenhouses where our tomatoes and tropical fruits are grown in winter and that sort of stuff. We've realised what a great benefit it is to agriculture and horticulture, increasing carbon dioxide levels. It's a tremendous improvement, it gives a tremendous improvement to our agricultural production. And so a lot of this carbon dioxide is actually doing too many good things almost. Okay, I want to now look at the way that greenhouse gases actually do what they do. Or in fact, I'm going to expand it a little bit. I'm going to go over the way that the Earth controls its own temperature. We've seen that the temperature out in deep space is minus 200 and something degrees Celsius. It's pretty chilly. But yet down here, we're able to get around in t-shirts in winter in Sydney. A lot more comfortable. How does the Earth do that? How is it that the Earth captures just enough heat to maintain this nice temperature balance? How does it get rid of the excess temperature? Okay. Well, this is all supposed to automate at its own time. Okay. What we have here, notionally this time, go. My automations are going to be a bit messed up, I think. See if I can get that to go. Okay, it'll all come on. Okay, so much for the animation. Okay. With the heat that comes in from the sun through our greenhouse layer, it comes in and hits the Earth's surface. When we take a sober look at that heating, an important part of the heat which is taken off the Earth's surface actually doesn't go as a result of reflection. It goes as a result of something else. And to get you to think about what that something else is, I would like you to think about what you would do in your backyard if you had something really hot that you wanted to cool down in a hurry. Would you wait for it to simply radiate off into space? What would you do? You had something really hot in the backyard, something dangerously hot. What would you do to it to go and cool it down in a hurry? Put water on it. That's great. Okay. I'm glad you're wearing a tie. It sort of shows that you've got the brain working. It's fantastic. You put water on it. How much of the Earth's surface is covered with water? Yeah. And by the time you take the dry parts and you consider the rivers and the swamps and the moist kind of rainforests, and even the washing flapping on the clothesline out in the backyard. Okay? There's an awful lot of wetness on the planet. Over 90% of the heat that lands on the surface of the Earth is not reflected. And in fact, one of these slides had a photo of what the Earth looks like from space. The water on the Earth doesn't look like a mirror from outer space. It looks black. That's not a very good reflector. But when the sun's heat gets onto the ocean's surface, it warms it up, causes evaporation. Off the surface of the Earth, something like 640 cubic kilometres of water evaporates every year. That's an awful lot of water, 600 and something thousand cubic kilometres. That takes an awful lot of energy to evaporate. It turns out that accounts for well over 90% of the Earth's of the sun's heat, which actually leaves the planet. And that leaves because the water is evaporated, the liquid on the ocean, or maybe on your underwear that's kind of drying in the sun, then turns into water vapour. The water vapour then rises through convection, and it rises up actually through the greenhouse layer, up above the greenhouse layer, where it cools down. It cools down. Now what happens when something cools down? Okay, it loses heat. Where does the heat go? It's radiated away. Now this is radiant heat above the greenhouse layer. The greenhouse layer is probably going to stop the heat from coming back down to Earth. So it's being radiated out into space. So 93% of the heat energy that lands on the surface of the Earth rises up as water vapour through the greenhouse layer, which is mainly water vapour anyway, up above it, where it radiates out into space. When it radiates out into space, it gets cold. What happens to cold gases? Do they go up or down? Comes back down. They come back down, they cool down, they clump together and become clouds, rain falls out of the sky, and the water's back on the surface again. That's the water cycle. You guys have been introduced to the water cycle probably from primary school or something, or whenever you first did science. 640,000 whatever cubic kilometres of water does that. That's something like over 90% of the heat that ends up on the surface of the Earth. Nothing to do with carbon dioxide at all. We've already seen on a previous slide that even the greenhouse layer itself, carbon dioxide is only a very small player. There's another aspect of this global warming, which is a bit of a curiosity. I think we've already seen that we need the greenhouse layer to make the Earth's surface comfortable. Scientists such as John Wharton, I mentioned earlier on, who was telling us that we have to reduce the population in order to control the Earth's temperature. He gave this little graph over here of what's called the phase diagram. If any of you guys did sort of maybe 3-unit chemistry, and you may have come across this at school and high school. Phase diagram. Two things that Horton noted. One was that on the planet Venus, they don't have any water on the surface. They have a very dense greenhouse layer made up largely of sulfuric acid, not a very pleasant place to be. Because of the intensity of their greenhouse layer, not very much of their temperature, their heat coming from the sun, escapes, and so Venus is an extraordinarily hot planet. Not merely because it's a little bit closer to the sun, but largely because of the intensity of its greenhouse layer. On the other hand, Mars, which is a little bit outside Earth's orbit, a little bit further away from the sun, but not by that very much, it has no greenhouse layer at all, greenhouse gas layer. And it has no liquid water on its surface because it's all frozen. And now that we've been up there exploring with our space sort of vehicles and so on, we know that it does have water on the surface, but it's all ice. But because it's got no greenhouse layer at all, the surface of Mars is extremely cold. So you can't live there either. Where does that leave Earth? Well, Earth is curious because it's unique, because Earth has liquid water in it. And Horton actually gives the phase diagram. As I say, it's a familiar diagram for people who don't do science. Okay. What he's telling us is that it's the liquid water on the surface of the planet Earth which actually enables us to have the temperature we do. And of course, if we fiddle with it, cause more carbon dioxide, more water vapour to be in the atmosphere, we're going to get a bit more like Venus. If we have a bit less, we're going to get a bit more like Mars. Okay. So that's kind of a curiosity. The other curiosity with Venus and Mars is that we have discovered over the periods we've been able to observe them really, really carefully, that they have planetary temperature changes which are very, very similar to what's been happening on Earth. That's curious, because if our temperature has been changing as a result of our carbon dioxide production, and we're going to be doing all sorts of dreadful things to our lifestyle in order to reduce our carbon dioxide production in order to control Earth's temperature, how is it that Venus happens to be getting warmer at about the same rate as the Earth? Maybe our carbon dioxide is seeping over to Venus or something. Even worse, Mars is doing the same thing, cold as it is. It's been warming up at about the same rate as the Earth over the period we've had satellites going up and looking at its temperature. Very weird. However, I hope by now I have at least rattled the cage a little bit as far as the science of what we're talking about. Okay? Our concern about reducing the energy consumption of buildings, green star ratings on buildings and so on. Why are we doing that? I've been taunting students, PhD students, and presenters at conferences now for about 20 years saying, can you tell me what impact on the Earth's climate our green star ratings are going to make? And while people are able to tell you how important it is for the property industry that we make green buildings, nobody in the last 20 years has been able to tell me what impact a green star rating of 4 rather than 3 is going to make on the planet's temperature. It simply doesn't happen. Nobody has studied it, or at least those people who have either are too embarrassed to tell the world or haven't been able to publish because it's very difficult publishing if you're not carrying the company line. And this is where it gets into politics. A number of years ago now, a prominent American politician made himself very famous and a little bit richer by producing a movie called The Inconvenient Truth, where he showed how we're all going to die as a result of carbon dioxide and the fact that we weren't riding bicycles. The only problem was that this documentary, or supposed documentary, which was supposed to be showing the science of the climate problems we have at present, is not able to be screened to school children in England as a science documentary, because an English court has found that its only merit is as political propaganda because its science is so bad. The politics gets a little bit more interesting. The custodians of the global temperature measurement is done from a university in British Isles, University of East Anglia, and a little while ago, a fair bit of their email communication was released to the world. One of those inconvenient pieces of whistleblowing, where the scientists collecting this information and showing it to the world were discussing amongst themselves the tricks that they used in order to create the illusion of the Earth's rising temperature and its connection to carbon dioxide. It's sometimes been called climate gate. Again, this stuff is history. And the curious thing is that not a lot of people talk about it, even though at the time it represented extraordinary scientific fraud at an absolutely huge level. If we go to the web pages of organisations like the Australian Greenhouse Office, the UN organs for UNBC, all that stuff, what we find is that a lot of assertions that don't stack up with science. One that came out again a little while ago now was the claim that the great majority, the overwhelming majority of climate scientists believe in the global warming theory. The only problem was that when people actually drilled down and looked at this consensus, they found that people were being signed on to agreeing with the consensus merely because they wrote back to the UNBC saying they didn't agree with it. And they still got sort of put in as part of the consensus, which got a little bit frustrating for some people, and some of them tried to sort of talk about it. However, we still talk about it. Overall, in recent times, we've got to the stage where we don't talk so much about global warming anymore. And I mentioned that the high temperature on the planet was about 1998. Yep.
I'm just a little bit concerned because you showed us some blog posts and some graphs, but you haven't actually mentioned a peer-reviewed author at all on this.
Oh, McIntyre McKittrick, peer review. I can give you a number if you like. In fact, I think at the end here there is a short bibliography as well. Good. We'll move on to sea level rise. And I mentioned that sea level rise, it was something that in 1970 was going to be about 1.5 metres, 1.6 metres by the end of the century. It turned out to be somewhat less. It didn't stop people in the 1990s and following from talking about the alarming sea level rise and what we had to do about it. And you folks have probably been introduced to some of the concerns in that regard. If you look at the current predictions, there's a number of computer models that range in both, when the CSIRO looked at it, they collected all of the findings and they said that they vary in both degree or magnitude and direction. Some of the modelling shows the sea level actually falling, most violent rising. The most likely rise will be probably no more than about half a metre, about 40 centimetres over the next century or so, as far as we can tell from the current computer modelling. That doesn't stop us from being, let's just take a step back. From a property point of view, let's look at what a sea level rise of, let's say, half a metre would make around Sydney. Okay. When you look closely at it, this is going to happen over a century. What's the economic life of our current buildings? If we were to develop a building today, what economic life would we expect from it? Any suggestions? You guys should know this, the answer to this one. What's that?
40 years.
Yeah, 40 years is the norm. I was a little bit surprised once. I was doing some consulting work for some people building retirement facilities, and they were using a 25-year economic life. And I thought, oh, that's a bit rough. But for various reasons in that industry, they prefer to pull buildings down in 25 years. But about 40 years is common. Now, why am I bringing that into the discussion? Because if it's going to take a century for sea levels to rise by 40 centimetres, about it means that that's going to be the economic life of 2 building cycles, which really gives us adequate time to do some management controls. In the past, humans have proven themselves quite adept at coping with slow and gradual changes. Where are they? The dikes, in Holland, that's right. It's a good example, where they're keeping the ocean out for differences in sea level of considerably more than half a metre. So the suggestion is that from a property management point of view, we have a long time to accommodate for sea level rise if it happens. During that time, it's going to be quite straightforward to be able to manage it in such a way that we can either raise our floor levels by half a metre or what have you, or put some kind of control mechanism in, like sea walls or whatnot. So we're only talking about half a metre, and we've got about a century to build it. Is it a huge problem? Probably not. This is when we move into the importance of the green buildings, the Green Star approach. Because our whole approach, or our whole push towards green buildings is premised on the assumption of human-caused global warming, anthropogenic global warming. When we try and connect our Green Star ratings to actual environmental outcomes, when Tim Flannery was asked about this, who is kind of one of Australia's current leading apologists for the global warming proposition, he said that it's going to take us something like about 500 years before we see any results at all. What that means is that for the next 500 years, we're going to have who knows what changes, but it won't make any difference to the planet temperature at all, even if everyone on the planet was to come on board. I would suggest that if we're so concerned about the future that we're going to do something which is at best scientifically questionable, but what even its proponents say is not going to have any impact for about 5 centuries, we're probably doing something which is a little bit short of genuine scientific justification. However, to overcome that, we have what's called the precautionary principle. The precautionary principle is the idea that even if I'm not sure of a bad thing likely to happen, it's a good idea to manage things so it won't happen anyway. And that's a reasonable approach. I may not be too concerned about, a burglar coming into my house tonight, but I'll still lock the house up. And so I'm taking, if you like, a precautionary approach. I don't like it when these animations go the wrong way. Okay. I don't think this is going to work. Let's talk through this. The precautionary principle is reasonable and prudent when the costs of the precaution are low and the relative likelihood, even though it's risky, is relatively high. If I have something which is likely to be very expensive and awkward to do, to overcome a problem which is extremely remote, the precautionary principle is probably not very sensible. It's very easy for me to lock my door at night when I go to bed. Doesn't hurt much, doesn't cost much. If I was to apply the precautionary principle to the likelihood of Martians melting my house with some ray from outer space, and so as a result of that, I built a concrete dome over my house, okay? People would probably consider that my application of the precautionary principle was not very prudent. So I might spend millions of dollars with my Martian-proof dome, and it might be very difficult to live with. And have I really dealt with a likely danger? Not likely. So that's the point here, and as I say, the animation is going to mean that most of the text on here is going to get forgotten. Okay. A few points. Firstly, I think this matter is still an interesting scientific question. When David Evans was working for the Australian Greenhouse Office and poring over the data, it was an interesting and live question. That's now some years ago. It may be that there is something going on that we still don't understand. However, we have progressed to the point there is sufficient information that it appears unlikely to be settled science. It's not something that we know with certainty. So let's imagine that there is a possibility that something's going on. Do we have the data and the complete confidence to be able to, go ahead and do whatever is likely to, be required? The answer, in many people's opinion, is not likely. What we need to move towards is a point where property markets are not going to be unnecessarily balanced or biased by something which is simply not completely understood at this stage. I won't go any further into why we're in the world we're in. There is an awful lot of money to be made from a number of these problems, but that's a story for another day. I think we'll leave it there. Let's move on to the last page. Which gives us some of those citations, as a number of others we added in there as well. Thank you.